No.
Sorry to put those right in front of your desk over there. Sorry, Ivana. So let's do this. Where are the remaining stacks? Are those the tests? Let me have all this stuff here. I'm going to just pass these. Oh, these are all yours?
Yeah, that's
okay.
all
Oh,
files for me.
that's your table. Okay. Here, have you gone through these? These are exams and other stuff. So go ahead and sit down, take those, and you can go through those. Is this other stuff? Go hang tight. Have a seat. I'm gonna pass these around. All right, here. Thank you. All right. All right, we need to get class started. I have all your stuff, old things that are going to be passed around. But we do need to get going with today's material. The exams are getting passed around. Watch my projector here. Here, Kiki. Ivana? Vanessa, your exam's here. Joshua, Ruben. Joshua? Ruben's not here. Okay, so I sent an email out, I believe, Thursday night on the results for exam 2, right? And it had a summary of the class average and all that good stuff. I don't remember what the class average was, 75? 75? 5 A's, 8 B's, 5 C's, 5 D's, 2 F's. That's the way I remember it. And that was before any curves, or not curves, bonuses. I did add bonuses today, so all the grades should be pretty accurate. And we proceed. Okay? So, y'all ready? Yes? If you have any questions specifically over the exam, just get with me in my office hours or something. Yes?
Are you going to post a key, like the solutions on it? So we can look over it.
I don't know if I'll post them. If you want to look at my key after class, I don't mind you looking at my key. I have it right here. I don't know if I'll post it, though. So if you do have any questions about how I graded something, let me know. I decided to grade every single problem out of 100 points. So if you have a problem, it says 100, that means you got full credit for it. 50, it means you got half credit for it. There was one problem in particular. I think it was number 5. Was it the one with the e to the x over 1 plus e to the 2x, that one?
Yeah.
Only a few students got that problem. And I think the lowest that I gave anyone was maybe a 50 or a 40. Like even if you didn't do anything on it, I think, unless you left it completely blank, and then it would be 0. But if you tried something, I think the minimum I would have given would have been like a 40 or a 50. Because I didn't want that problem to like totally destroy you, right? But you had to try something for it. All right.
What if my tears were on the paper?
If your what was?
My tears.
Your tears? I didn't see them. There weren't enough of them.
Well, I tried something, but I'm just, for example, like if your tears were on the paper, would you have gotten credit?
If it was wet and damp, I could tell you were crying.
Yeah, 5 plus 5.
All right, let's do a quick review of the definite integral in the fundamental theorem of calculus that said that this was equal to this, was equal to this, right? And geometrically, this meant that if we graphed f, little f, that capital F of b minus capital F of a would represent the area between the function and the x-axis, right? Yes? Well, what we're going to do now is we're going to, instead of looking at the area underneath one curve like this, like we were doing, here's some function f, and we're looking just below that function from a to b. Instead of just looking at that area, we're going to look at the area between two functions. So you have, let's say, a function f, and then you have some other function, let's call it g, which is below f. So maybe g does something like this. I don't know. Doesn't really matter what g does. As long as g is below f on some interval. So let's say we look between here and here, again, a and b, and we want to know the area between them. Understand the difference between the two problems? How do you think I can actually compute that area? Get them both and subtract them? So you mean find the area under f first, which will be all the way down, and then find the area of g below g, and then subtract the g from the f, right? Does that make sense that that would work? Okay, and that's exactly what it is. So imagine that the area under g is this. The area under f is everything down. If I take the blue part away, I'm left with the red part. Yeah? And so that's exactly what the beginning of this section is about. And we have a formula for it. Where is it? Right. Yeah. Let me try and zoom this out, or zoom in on this a little bit. Suppose you were given two functions, f and g, where f is bigger than g, right, on some interval a, b. Then the areas, I don't know why that says areas, it should just say area. The area between the curves is this integral. So you're just subtracting the two functions. And that's okay to do, right? Because if you subtract two functions in an integral, it's the same as splitting it up into two, isn't it? Like if I do this, that's equivalent to doing this. Right? Because with subtraction in an integral, you can split it up into two. Now, if that was multiplication, no go, right? But it's subtraction. So this is the area under f. We're going to take away the area under g, and that should be the area between the two functions. Now, in my notes, I mentioned that this formula works when you have vertical rectangles or functions of x. It's like, what the hell is he talking about? Vertical rectangles, functions of x. I'm sorry? Let me draw a picture, okay? I'm going to draw a picture. So please recall, going back to our basic formula, let me go back to just f. when we were doing that in the past, I said I wanted you to understand that each of the symbols in this definite integral represented something. Do you all remember what the integral actually took the place of? It was a sum, right? It was a sum of an infinite number of rectangles. And those rectangles, weren't the rectangles determined from those two things? F of x represented what in the rectangle? The height, right? And then the dx was the width of the rectangle. So geometrically, here was our picture. We're looking at the area. We could imagine taking an infinitesimally small rectangle like this, right? If we take that infinitesimally small rectangle and we blow it up so we can see it over here, right? The bottom of the rectangle was the x-axis, right? This right here is the x-axis. What's another way that we write x-axis? Because it's a horizontal line. What's another way I can say x-axis? As a horizontal line, what is it? Y equals 0, right? So this is the same as y equals 0, right, on the bottom. And on the top of this function, sorry, this was supposed to be an arrow. On the top of this function is this blue curve, which is the f function, right? Imagine that f function comes in here like this and creates the top of my rectangle, yeah? So this up here is my f function. And the bottom function here is really what? What's really the bottom function in our original integral before we started with today? What would the bottom function of this rectangle be? 0, right? G of x is 0. See, the bottom of this is g of x equals 0. I don't know if you're following this or not, but what I'm trying to tell you is that we have been finding the area between two functions. We've been doing that, but I just never told you that the bottom function was actually the 0 function. Now what we're going to do is we're going to move that 0 function to be something else, right? But we have rectangles in our picture that creates this. Our rectangles are vertical, right? These are vertical rectangles, yes? What we're going to do after this is our rectangles are going to be horizontal, and you'll see it's going to change the way things go. All right, so we have kind of an upper function and a lower function, right? If you can determine the upper function and lower function, you plug into the formula and we're in business. You also need to know the endpoints, right? Where you're going to start and stop. Okay, so now what I'll do is I'm going to adapt that picture just slightly. And now I'm going to bring in the other function g. And here's my picture. So I'll bring f in again with blue. I'll bring g in. I'll do g in red. And let's say that I want the area between those. So does it make sense to you that I could create a rectangle in here like this, and I could find out the area of that rectangle, and then just take an infinite number of them, and that would create get that area right in there? Yes? Now, look, if you're looking at me right now going like, I got it, I understand, you don't need to explain this anymore, I've got it. Trust me that I'm only trying to really get into the visual part of this for what's coming up, all right? So we've got this little rectangle in here. What I want you to do is imagine taking that rectangle to the side here and just taking a look at it, identifying the x-axis, okay? And then let's label some things here. We've got the blue parts there. The blue part's on top and the red part's on bottom. This is the f function here, and this is the g function here, yes? So how tall is the rectangle? How tall is this? What is it? How tall is just the rectangle from here to here? It would be the height of f, right? Take away the height of g. So this would be f take away g, yes? The width of the rectangle would be, what do we always use for width here? dx. And so the area of that little sliver, what's the area of this little sliver? F minus g, right, times dx. And that would be the area of one of them. If I want to add them all up, I throw it into an integral, and I go from a to b. Now, a to b would be where these two intersect, right? That would be our a to b. And so you can see, hopefully you can see, where this formula comes from in the picture. Do y'all see it or not? Yes? Okay. So anytime we're asked to find the area between two curves, we will have to be able to determine which function's on top of the other. We're also going to have to be able to determine where they hit each other. Once we do that, we just set up the integral and we go to town. Right? Questions? Let me do an example. Say, as an example, first example, let's find the area find area between y equals 5x minus x squared and y equals 2x. I should mention to you now that we're in chapter 7. There's going to be a lot of graphing going on. So I would bring your graphing calculator if you have one from here on out, and be ready to be faced with the challenge of graphing a lot of different functions. Polynomials and rational functions and trig functions, and so all that stuff that you studied a long time ago is going to start to peek its head out again. All right, so let's see how much of this we can do without a calculator. All right. First, we need to figure out what the heck area they're talking about, right? So let's try and graph this. Do we know what y equals 2x looks like? Yes? That's a line. Slope is 2. Y-intercept, 0. So I hope that everyone would be comfortable drawing, let's say, go out 1, up 2, so up 2 over 1, something like this. And I'll do it in a different color to make it a little easier to identify. Is that right for slope? Up 2 over 1? Yeah? This looks like this. On your exams, you will be asked to graph these in detail. It'll be graph the region, sketch the region between these two, find the area. So I'm going to expect a nice, pretty picture at the end of it all. All right, that's y equals 2x. Let's label it. Let's also label our x-axis and our y-axis just so we're aware of the way things are oriented. How about 5x minus x squared? What is this? What does that look like? 5x minus x squared? It's quadratic. Quadratic functions look like parabolas. This particular parabola opens which way? Down. Why? Because there's a negative in front of the highest power of x, right? So we need to figure out where this is. All right. Come on, I need your help. 0, 0, good. Okay, so you're just giving me a point. You recognize that 0, 0 is on this graph? Who said that? Okay. Thanks, Sean. I'm kidding with you. I'm kidding. I knew it was you. I know your names now. You're Sean. I know that already. 0, 0, right, Matthew? 0, 0. That's on my parabola. 5, 0 is another x-intercept. So if you set this equal to 0, you get two answers, 0 and 5. I'll let you do that yourself. So the other one's out here. 1, 2, 3, 4, 5. And it opens which way? Down. Now, there are a lot of things that could happen here. It could do this. You know, it could go up further. I need to figure out where it is, like exactly where this thing is. So do you know how to find that highest point? How do you find the highest point on that parabola over there? Anybody know how to find the highest point on this parabola? Yes? Go ahead. Ron's got an idea here. Plug in what? Well, do you know it's halfway between these two? Is your vertex always going to be halfway between the two x-intercepts? If it's a parabola, it will be. It will be. Yes. But let me go back to something else. Back in, what was that class that you took before this? Oh, Cal 1, right? Do you remember if you wanted to find the highest point on a parabola, that corresponded to where the derivative was 0? So couldn't you just take the derivative of that real quick? What's the derivative of that? 5 minus 2x, and then set that equal to 0, and you get 2.5. So you actually know that it happens at 2.5, don't you? And then you could take that point and you could plug it in to figure out how high it is. 6.25? Okay, so this thing is really starting to irritate me, that little rag. So at 2.5, 1, 2.5, I go up 6 something. It's up here somewhere. And this parabola opens down like this and goes like that, like that. Everyone understand? That's my graph without a graphing calculator. Where's the area that I'm talking about? Where is it? It's between the two, right? Between the two functions. So we're talking about this area. We want to know that area right there. We don't want to know this, right? The reason we don't want to know this is because this area is not bounded by both of those curves, is it? This x-axis is not enclosing that region. This x-axis isn't really even there. The parabola just keeps opening up. So we're looking for the area between the two. How about over here? How about this area? This area is between the two. But it keeps opening up, right? There's no close. It's not a closed area, right? So this is the only region in the entire graph that's enclosed by both curves. Agreed? Okay. So can you tell from this picture which function is on top? The blue one, right? So the blue curve is going to be f, and the red curve is going to be g, right? What else do I need to determine? The starting and the ending point, or start and the stop of the actual integral. I can tell by the picture, where does it start? 0. But I can't tell where it stops. I actually have to figure out where those two functions intersect, right? And how do you figure out where two functions intersect? You set them equal to each other, right? So what I need to do now is determine the intersection points. Find intersection of f and g. To do that, I set the two equal to each other. F of x, 5x minus x squared equals 2x. So how did you solve that? You have some options here, right? 0 equals x squared minus 3x. Move everything to the right side. On the right side, factor an x out. And you get two solutions from this, right? 0 and 3. We already knew about the 0, didn't we? Now we know the other one was at 3. So x equals 0 and 3. Those are our intersection points. So do we have enough to set up the integral now? Yeah? Think so? Well, okay, let's do it. The integral will go from where to where? 0 to 3 of the first function, which is the one on top, which is which one? 5x minus x squared. Okay, minus the second function, dx. Now, I should put all that in parentheses again, but I want to stress this is my f, this is my g. I'm putting them in parentheses even though I don't necessarily need to. That would be more useful if g had more than one term in it, right? Because then I'd have to distribute a negative through. But that's it. And then I'll clean this up. This is equal to integral 0 to 3 of negative x squared, then what? How many x's do I have there? 3 x's? dx. Five x take away 2x, 3x, right? Can you do this integral? I hope so. Shall we? It's our first one. We'll do this one all the way. This is equal to negative 1/3 x cubed plus 3/2 x squared, evaluated like that. So you just find the antiderivative of each one, right? And now we go and we plug in. You do the 3, I'll do the 0. How about that? Sound like fair? I'm done. Are you done yet? I got my part. All right, let's go. 3 cubed, 27 divided by 3, 9, negative. So negative 9. And then 3 squared, 9 times 3, 27 over 2. So plus 27 halves. And then you put those two together. It's 9 halves. 9 halves. 4.5. So the area between those two curves is exactly 4.5 units, whatever the units are being measured in. Could be miles, inches, whatever. Do you all understand the basic concept here? There's no magic happening or anything here. Okay, let's do a similar problem. Let's do area between y equals 1 over 1 plus x to the 4th and y equals 6x squared. How about we graph 6x squared? 6x squared is a parabola, right? Opens up. So it looks something like this. Yeah? What about 1 over 1 plus x to the 4th? What does that look like? It's a rational function. What is the value of this function at 0? 1. What is the value of that function at 1? It's 1/2, right? What's the value of that function at negative 1? 1/2. What's the value of the function at 2? Uh-oh. 2 to the 4th plus 1. Isn't it getting very small? As you go to infinity, this thing gets smaller. The whole thing gets smaller, doesn't it? So what happens is as I go out to the edges, this thing starts to flatten out, doesn't it? So it looks like this, almost like a bell shape. You could graph it on your calculator, but I don't think we need the graph from the calculator to be able to finish the problem, do we? Do you think we do? Can you tell which one's on top, which one's on the bottom? Yeah? So there's the region, right? The function on top, this was, the blue was y equals 1 over 1 plus x to the fourth. The function on top should be the f1, right? And the one on the bottom should be g. What do I still need? Their intersections, right? That's going to be the hardest part of this problem, is finding their intersections. Because what do you do to find their intersections? You set these equal to each other, don't you? All right. So the intersection you set 1 over 1 plus x to the fourth equal to 6x squared. And how would you like to solve that? Multiply both sides by 1 plus x to the fourth, which will make 1 equals 6x squared times 1 plus x to the fourth. I'm going to distribute and then move it over. Yeah. 1 equals 6x squared plus 6x to the fourth. 6x to the what? Sorry. 6. And then bring the 1 over. So I'm going to put it in order. 6x to the sixth plus 6x squared plus, minus 1 equals 0. What do you think? Dun, dun, dun. Right? Dun, dun, dun. How do you do that? It's not a quadratic, right? It's not. What are our techniques for solving polynomial equations? Let's talk about it. Let's do a recap. I'm not going to write it down. Let's just talk about it. What are your techniques for trying to solve something like that? Or even just trying to factor this side? You've got, hoping it's a quadratic, you might be able to use quadratic formula. Or a quadratic type. Quadratic type would be something like this. 6x to the fourth plus 6x squared minus 1. That would be quadratic type because the x to the fourth is doubling the power of the x squared. You might remember this also. You could have done like x to the sixth, and this would have been x cubed. That's quadratic type. Or if this was x and this was square root of x, then that's quadratic type. But you have to have this one being this one squared. That's not happening here, is it? So we can't use this as a quadratic. That's not going to work. How about the rational zero test? You all remember a rational zero test? Where you do synthetic division, something like that? No? Well, it's not going to work here either. So it wouldn't work. It would fail. So when we're looking at an equation like this, one thing that we could try, if we can't solve it algebraically, is just doing it by inspection. Just try a number and hope for the best. Because sometimes it's that simple. But I don't think it's going to work. If we try like 1, will 1 work? No. -1 won't work either. So we really don't have an easy way to find these. Do you all agree? We're limited here? We're limited? Now, how many from your Cal 1 class, how many of your instructors covered what's called Newton's method? Anyone remember Newton's method? We did a little bit, right? Not super in-depth, but Newton's method? Okay. Newton's method is the way that a computer solves equations. And it's an algorithm. It's written into the code. When you go to solve an equation on a computer, it applies this algorithm to the equation and it gets to a solution. So with a problem like this, there's no algebraic way we could solve this. I would not give you a problem like this on a test. I just wanted you to see and be faced with an equation that would not be easy to solve. So we have two options here at this point. We can either get onto Wolfram Alpha, and we can have Wolfram Alpha give us the solutions, because there's got to be solutions, right? I mean, look at it, my picture. There's got to be two answers. Or we can create our own interval and make up our own and not look at where they intersect, just cut it off wherever we want. So I'm going to choose to go to Wolfram Alpha. Y'all like Wolfram Alpha, right? Guess not. So what do I do at Wolfram Alpha if I want to solve that equation? Type in 6x, what is it, to the 6th? Plus 6x squared minus 1 equals 0. That's all I have to do. It's like magic. The real solutions to this are negative 0.40297 and positive 0.40297. Sound good? So the solutions here, x equals negative 0.4, how about we round that, 0.41? And x equals 0.41. Does everyone understand? I would never give you a problem like that on a test where I sit there and I give you a problem, an equation you can't solve. Yes?
Is there a way to do that by hand?
You could apply Newton's method to it by hand. But that would, that's what the computer is going to do. So it would be tedious. It could be done. It would be tedious, though. All right. We good? So I'm going to set up the integral now. Is that correct? What's my top function? What's my bottom function? You remember what the top one was? It was the 1 over 1 plus x to the 4th, wasn't it? So 1 over 1 plus x to the 4th. And then this one over here was 6x squared. Yeah? Yes?
I had a question.
Uh-huh.
You told us whenever the limits are the same and one's positive, one's a negative, shouldn't we also check for whether it's an odd function or an even function? If it's an integral?
We could, yes, but think about the geometry of the picture we drew. Do you think the area is going to be 0? Right? Because now had it been, that was because it was symmetric. This is actually an even function. They're both even functions. So, but yes, if we would have drawn something, and had, let me see if I can do this, something like, I don't know, that's not going to work. Where that's not going to work. But this area and this area cancel. Then yes. But I'm glad you noticed that. Yes, we could think odd, but in this case it wouldn't. It wouldn't be odd. All right, so we would break this up, right? We don't really need the subtraction. That was just, again, to stress f minus g. And then you would integrate each of these one by one, right? Can you integrate this one? Can you integrate this one? Yes? It's x to the fourth. U sub is x squared. Where's du? Because du would be 2x, wouldn't it? Ooh, this one's trouble. This one's trouble. Okay, so we're not going to integrate this. We're stopping anyway. Okay, now the reason we're stopping, all right, the reason we're stopping is not because I'm trying to throw a nasty problem up here. It's that from here on out, I'm not going to go any further than the integral. Because the integral is what we spent all this time being able to do. Now it's just a matter of can we set the integral up. If we set the integral up, then we hopefully could get it. We're not going to spend time trying to figure that out. Understand? So on your test, I will give you problems where I will say, set up the integral that represents the area between these two curves. And you set the integral up. In some problems, I will say, set up and evaluate. So I want you to go the whole way, but it'll only be like one problem, maybe two on the test. Just so you can just show me you know how to evaluate an integral. But really, this is all about setup now, okay? All right. Now, I'm wondering if I should give you another one. Yeah, let's do one more. Find the area. You know what? I think you're ready to move to the next topic. How about this? When we draw a function like this, and I write here f of x, we say that that is a function of x, right? Because it passes the vertical line test, yes? But if I drew something like this, could you call that f of x? No, because it would fail the vertical line test, right? So this is not a function of x. But could I call it a function of y? Could I call it, let me use the same letters, hold on here. Yeah. Could I call it f of y? So what you do is, we know we have vertical line tests when we're looking at functions of x. To check if something is a function of y, it's actually a horizontal line test. But it's not the inverse. We have to be a little careful. That's what we check. For a function to have an inverse, we check a horizontal line test. But to see if a function is a function of y, we're basically running the vertical line test with our head turned sideways. That's what we're doing. So if I give you a y value, can't you determine the x value? It's the opposite of this. This one, I give you an x value, and then you come in here and you determine the y, right? X goes in, y comes out here, right? X in, y out. That's what a function of x means. This one is opposite. Y in, x out. Give me y, I give you x. So let me show you an example of each scenario here. F of x equals x squared, right? That is a function of x. I give you x, you give me y, yes? I give you x is 3, you tell me y is 9. This one over here would have to look like this. F of y equals something like y squared. I'm not saying that these are the pictures of these, okay? Just trying to get you to see the difference in the notation. If you have a function of y, then your variable in the problem is y. What this allows us to do is handle situations where the region we're looking at is not a function of x, where it's something like that. We can still find areas. So that creates a new formula for finding areas between curves. And this time we say we have horizontal rectangles instead of vertical rectangles. So let me draw the picture on the board here for you. And then we'll look at the formula. So here's x, here's y. Let's say I start with some function of y that looks like this. Is that a function of y? Yes. Not a function of x though, right? Okay, then let me come in here with a function, another function of y. That's a function of y, not a function of x, right? Then if I want to find the area between these, if I want that area in there, then can I draw a vertical rectangle? A vertical rectangle. Why won't a vertical work? Let's see, if I do this one right here, that vertical rectangle, do you have a distinct top and bottom to it? Well, the top is the red function, the bottom is the blue function, right? So that's okay. But you've got to have infinite number of these rectangles in here, don't you? And what happens when you try and construct this rectangle right here? The bottom function is the same as the top function. And so when you go to subtract the two, you get 0. There's something wrong there, isn't it? So you can't draw vertical rectangles in here and hope to get an area. I hope you see that. On the other hand, though, if we draw horizontal rectangles, then we can. Because if I draw a horizontal rectangle in here like this, will the blue one be to the right of the red one the whole time? Imagine moving this rectangle up and down anywhere you want in here. The blue one will always be to the right of the red. And you'll never have blue on the left and right at the same time, or red on both sides. So that rectangle is well defined. What is its area? So how long is this side of that rectangle? Well, I should probably label some things here, huh? How about we call this blue one f of y? We call this red one g of y? Now, with vertical rectangles, it was easy for me to say top and bottom, right? The one on top, the one on bottom. With this picture, we almost have to turn our head sideways and look top and bottom like this. Or if you would like, instead, the function to the right minus the function to the left. So what is that distance?
Sorry, the right's always going to be considered as the top.
As the top, yes. And the reason why is because this direction is positive on the x-axis, where on the y-axis up was positive, so to the right is positive, yes? So what is this up here? What's the length from here to here? Is it f of y minus g of y or g of y minus f of y? It's f of y minus g of y. How thick is this rectangle? Or what's the little infinitesimal thing? dy. It's dy this time. Now the reason why it's dy is because, remember dx was our change in x for a vertical rectangle? Well, if we're sideways, then going back and forth this direction, those are changes in y, aren't they? So dy. So the area of this little piece is f of y minus g of y times dy. And what do I want to do with all those rectangles? Add them up, an infinite number of them, right? So I can bring in an integral. And where do I integrate from? The intersection points, right? But am I going to look at the intersection points and find them on the x-axis? The y-axis. So I actually want to know that point and that point. And I'm not going to call them A and B because I don't want us to confuse them with the A and B on the x-axis. So instead we call them C and D. And which one goes, is C on the top or the bottom? C is actually on the bottom, D is on the That sounded like it was coming from really far away.
Gets you every time.
C is on the bottom, D is on top. Why?
Because that's on top and that's on the bottom. That's a bigger value.
That's right. This is positive direction, right? It's 0, then 1, 2, 3, 4, 5, 6. And we have the number line the other way, A and B. Right? It's 0, and then it gets larger this way. So same thing here. C up to D. Make sense? What's really kind of interesting about this, and I don't know how y'all are going to do with this because it kind of feels like a Monday. Y'all are looking at me like it's a Monday. Is that if you take the picture that we had for vertical rectangles, F and G, A and B, right? If you take that picture, that area, we have our x-axis going out this way, our y-axis going out this way, right? That's the picture we had before. If I go here to this picture, let's see how many of you can follow this, and I go to the other side of the board, okay? So I walk out on the other side of this wall, and I'm standing, I'm suspended, right, in midair on the other side of this board, and I walk over, so here's the board, and I walk over here, and I turn and I look at it like this. And the board's transparent, I can see the graphs. Wouldn't that picture of me looking at it this way with my head turned look exactly like this picture?
Yeah,
Would it?
like, cut it out and do like this, straighten it up.
No, I turn my head. Look, like, as far as if I look like this, then this axis is going to go out this way, right? In the positive direction. This axis is actually here like this, in the positive direction. And I have this. That's going to look pretty funny on the video, right? Do y'all see it or not? Mirror? Well, maybe a mirror.
Suddenly turned into a session of interpretive dance.
What I'm getting at, what I'm getting at is something that will come up later. What I'm trying to get you to see is this. This is basically the same as this. I mean, it's the same concept. There's not a whole lot of difference here. And so much that I stopped talking for a reason. Hold on. No, we're going to do it the way we're doing it. We're going to keep doing it. I haven't even done an example. We're not going to change it, but I'm trying to get you to see something, especially if you're going to go on and do more calculus. All right, so look. This is our standard XY plane, right? That's the standard XY plane. If someone were to sit here and draw this, and we also assume that this is the positive X direction, the positive Y direction, right? That's the way we standard write things. If someone were to come here and be like, hey, you know what? I'm a rebel, so I rebel, right? That's the way I want to draw my plane. Are they going to mess up? Is the math going to go crazy and be all wrong now because someone wants to draw their axes like this? Not at all. Because all it is taking this one and reflecting it, right? That's all it is. So nothing falls apart. The universe is okay still. Now, what if they come over here and they say, you know what? I'm going to be even worse. I'm going to say this is X positive and this is Y positive. Have they ruined the world?
It's like,
It's just a rotation, right? It's just rotated by 360 degrees, or 180, sorry. Right? They just rotated it, big deal. All right, so screw that. I don't want to do that then. I want to truly try and mess you up. Let me see. Y positive, X positive. So what's that?
flip.
It's just a flip over, right? I mean, there's a way to flip that. Or better yet, this is the situation where I'm on the other side of the board looking at it that way. If I'm here and I go to the other side of the board and look at it that way, that's what I see. End of the day, it does not matter how you label your axes in two-dimensional space. You never actually screw up the space because there's always a way to get from however anyone wants to label their axes over to what everyone considers the standard. That's the standard, right? But if some person wants to do this, all is well. Now, in three-dimensional space, it doesn't work that way. So that's supposed to represent three-dimensional space. So imagine, I don't know how many of you have seen 3D space yet drawn out, but there it is. Do y'all see it? Okay. So the xy is actually the xy that we're used to, is now laying down on the ground. Right? It's actually laying down on the ground, and the z-axis is actually coming out straight out of the page like this. That's three-dimensional space. The corner of the room is three-dimensional space. So the corner of the room is the origin. The x-axis is coming out this way. Y-axis is going out that way. Z-axis is coming straight up. And that's this picture right here. Now, if I come in here and I change, someone else says, you know what? I'm a rebel, so I rebel. And they say y plus x plus z plus. Is the math going to be the same? No. There's no way to change this space into that space with rotations and translations and movements. You can't do it. You can never get our axes to look the same. All right? So in order to make sure everyone draws it properly, we have to obey the right-hand rule. Have you all heard of the right-hand rule? The right-hand rule? How many of you have heard of the right-hand rule? Okay, physics mostly. Right-hand rule says when you draw three-dimensional space, your fingers should always point in the direction of the x positive axis. So I'll do it here. Remember, this was x. This is the origin. The x positive is that direction. My finger should always point in the positive x direction and should curl towards the positive y direction. And my thumb should point in the positive z direction. That's the proper orientation for three-dimensional space. All right? If you do it different, our math is going to be different. So we all have to agree on the same convention as how to do things. So this one does not obey the right-hand rule.
Depends on how you look at it.
No, it doesn't.
Because what if that axis isn't coming towards us, it's going away?
Which axis? This one?
Yeah. Because you haven't labeled the other one, so this one could be going away from us and next because
I suppose you could maybe visualize and think that that's going into the board instead of out at us. I guess if that's what you're trying to say, yes. But I'm trying to get you to see that as the corner of the room.
Yeah.
So the sense of the corner of the room doesn't work, right? Fingers are, got to have right hand. I've got to go fingers down the x-axis, which puts me that way. And I try and curl to the positive y, and now my thumb's the wrong way. All right. So when you have two spaces that can be moved around and they're still equal to each other like two-dimensional space, then we call those isomorphisms. They're isomorphic. And then these two are not isomorphic. They're not. You can't just twist and turn and get them to the other one. All right. Whoa, I just went off a little bit. I'm sorry. But you got to see the right-hand rule. I remember a class I was in, I was like I was kind of arguing with the instructor after class. I was like, I'm using the right-hand rule. And I had my left hand, because I'm left-handed. I'm doing the right-hand rule, and she looks at me, and she's like, that's your left hand. All right. So let's see one of these in action. We're going to do example 5 there. Find area. Is it warm in here? All right, find the area of the region bounded by these three curves. and sketch the region. Here's the trouble you're going to run into on your calculators if you're just like, hey, I've got a graphing calculator, I'm going to be fine, I'm just going to graph everything, is that these are not functions of x. These are functions of y. So unless you know how to use the parametric mode on your calculator, you're not going to be able to graph these. If you'd like to know how to graph them using the parametric mode, please come by my office and I'll be happy to show you how to use that feature on your calculator. But it's not for here, it's not for now. So we have to do it by hand. So are we all comfortable that these are all functions of y? X is determined if you know what y is. Y goes in, x comes out. Y goes in, x comes out. Here, not so much. But that's just a line, isn't it? Okay, so let's try graphing all of these. Let's start with y equals 0, because that's the easiest one. That's y equals 0, the x-axis. How about x equals the square root of 2 minus y? Uh-oh. What does that look like? Well, if you don't know what it looks like, I mean, you know it looks like a square root function? Okay, you know kind of what those look like? Almost like little half parabolas? All right, just plug in some values then. Let's plug in,
-2.
how about 2? Let's plug in 2 for y. 2 for y. If we plug in 2 for y, 1, 2 for y, what should we get for x? 0. Do you see that's opposite of what we would normally do? You plug in the y value, it spits out the x value, left and right. Let's plug in 1 for y. What do we get if we plug in 1 for y? Square root of 1, which is 1. So if I plug in 1 for y, I get 1 for x. Yeah? How about if I plug in 0 for y? Square root of 2, what's square root of 2?
It's smaller than 1.
Bigger. 1.414 square root of 2. So here's 1, here's 2. So when I plug in 0, what did I get? Square root of 2? 1.4, so something like that? We okay with that? Could I plug in y is, I heard -2, I like that one, right? What's -2 if I plug in y is -2? Square root of 4, which is 2. So if I go to -4 on the y-axis, I will be at -2 on the x. And I kind of get an idea of what this is looking like now. -2, right? Sorry. That should have been here. At -2 for y, it's 4 in here. Square root of 4 is 2. So at -2 for y, I get 2 for x. I accidentally put -4. Yes, and it keeps going. I think that's probably enough for us to get an idea of what's happening here. All right, what about the next one? This is my blue one. What about the next one? Plug in 0 for y, what do you get? 0 for x. Plug in 1 for y, what do you get? 1 for x. Plug in 2 for y, what do you get? 16? Yes? Way out here, right? Somewhere way out here. What if I plug in -1 for y? And then -2 for y, way out here again, right? So this looks very much like a parabola, but sideways. It's not a parabola, that's 4th degree. So it looks like this. Oh, shit, I missed it. Oh well. Okay, good enough. We happy with that? Do you see the region enclosed by all of the curves? You sure you see it? There's 2 of them, right? y'all see them? So let's,
I was gonna say, can you do it without y equals 0?
yeah, you could do this without y equals 0. Let's change it. Instead of this, let's make this easier, y greater than 0. How about that? Because what does that do?
Yes, it's 11.
It basically cuts off the bottom half. Agreed? Y greater than 0 means we're only looking up here. So that'll force our region to be this and there, won't it? Questions so far on the setup? A good picture is always where you start with these. You got to have a good, decent picture to go. Now that I've got a picture, I'm actually going to spend a little bit of time trying to make my picture a little bit nicer to look at, just my personal preference. I realize that I'm in a small space there, so I can kind of zoom in on it a little bit. I have a bottom function, this. I've got this blue function that comes in like this. And then the black one looks like this. Right. Now, I'm only doing this to help guide us for the next step, which is to determine whether or not we want to do vertical rectangles or horizontal rectangles. Do you want to draw vertical rectangles or horizontal rectangles in there? Horizontal, why not vertical? Would vertical work? If I draw a vertical rectangle right in here, do I have a top and bottom function? Yes? And it's not the same function, right? It's not wrapping back on itself. So I could do that. But when I get to this point, what would happen? The rectangles on this side change a little bit because now the top function is actually the blue, not the black. Do you agree? Do you see that? So I could do it with vertical rectangles, but I would have to split it into two different integrals. I would have one integral that would take me up to this point, and then I have a separate integral that would go from that point over. Understand? That's too much work. If I do horizontal rectangles, one rectangle should take care of everything. Because the blue function will always be to the right of the black function, right? As I move the rectangle up and down, the blue is always to the right of the black. Right? So that makes sense that we would want to do that. Also, if we're going to use this horizontal rectangle, don't we need this blue function to be a function of y? And don't we need the black function to also be a function of y if we're going to go horizontal? And are these functions of y or x? They're functions of y, aren't they? So it's actually nice that they're already written this way for me. So which one was G? Is it this one right here? That was G. And then this one is F. What do we still need to resolve? The intersections, right? Where they hit each other. I need to see where these two hit each other. These two, right? At y equals 1, right? You can tell. You can tell just by looking. The intersection on the other side. You mean where they hit over here? Is that the one you're talking about?
Yeah, but we can't look.
We're not looking down there, but how would we find that, right? We would need to be able to find that. You would have to set y to the fourth equal to this. And then you'd have to solve this. So you would square both sides. And then you'd probably be in some trouble at that point. So you go to Wolfram Alpha. But again, this is something you could do by inspection. Just look. Y is 1, it works. Right? Y is 1, it works. It's 1, yes. But what's the other one? Because there's a negative solution also. Yeah, let me see if I have it here. Yeah, see, on my picture, that's the actual graph. I did go back and do it as y greater than 0. right, so is that all right with everyone that this one right here is going to be y equals 1? May I set up my integral? All right? Okay, where is it going to be from? 0 to 1. 0 to 1. Remember, 0 is this bottom piece, right? We're going from here to here. 0 to 1 on the y-axis. And then it's going to be something dy. So which one goes first there? The square root one, right? The blue one. Square root of 2 minus y. And then the other one, y to the 4th. You think you could integrate that? Yeah? Basic U sub on this one. Power rule on this one, you're done. But that's where we stop. So far, is this okay? Sketch the region bounded by these two curves. This is a good problem. Sketch the region bounded by x equals sine y. And find the area. Let's see. We have x equals sine y, x equals cosine y equals 0, y equals 2 pi. So we want to sketch the region that's bounded by all these curves, and we want to find the area of the region bounded by those curves. These are functions of what? X or y? These are both functions of y, aren't they? This is y equals 0 is the horizontal line, x-axis. Y equals 2 pi is the horizontal line up at 2 pi. So when I go to graph this, I'm going to draw x equals sine y. So let's see if you can do this. If y is 0, what's x? X is, what's sine of 0? 0. So for this one, if y is 0, x is 0. All right, let's pick some common angles that we're going to be able to know. What if, see, if this is 2 pi up here, this is pi. This is pi over 2. Do we know the value of sine at pi over 2? So if we let y be pi over 2, what is sine of pi over 2? 1. So if y is pi over 2, the x value is 1 to the right? What if I plug pi in for y? What's sine of pi? 0. So the x is 0. So up at pi, y is pi, x is 0. The next common angle that we should know is, what, 3 pi over 2? If y is 3 pi over 2, what's sine of 3 pi over 2? Negative 1? So the x value is negative 1. And then back at 2 pi, we're back at 0. So do you all see that we've drawn this sine curve that looks like this? That's what we've drawn. Now again, if you're outside on the other side of the board and you look at it this way, it's just the sine curve like you normally see it, right? It's just when we draw it as a function of y, it looks kind of awkward. All right, now we're going to do the same thing. we're going to do it for cosine y. So if y is 0, what's cosine of 0? 1. So when y is 0, x is 1. So that puts me here, right? When y is pi over 2, cosine of pi over 2 is 0. That puts me here. When y is pi, cosine of pi is -1, so we're here. 3 pi over 2, cosine of 3 pi over 2 is 0. And cosine of 2 pi is 1. So you get this picture. Like that. So see it? Again, if you're on the other side of the board looking in, tilt your head, that's cosine. So what we need to know now is the area between these curves. And I'll stop up at 2 pi, right? I start at 0, I go up to 2 pi. Does anyone see what the problem we're going to run into? What's the problem?
Most of it's negative.
With that, I'm hearing different things.
He said no.
I didn't.
It's a negative and positive areas.
Yeah, like if, well, I should probably back up. Are you going to want to use vertical rectangles or horizontal rectangles? Horizontal, right? I mean, there's no question about that. Do you all agree? So if you're going to go horizontal with your rectangles, if you look at this rectangle right here, which function is on the right side? Blue, right? What's on the left? Red. But when you get to the rectangle up in here, what? They switch places, right?
So you just gotta separate it.
So you're going to have to split this up. You're going to have to break it up into one integral that goes from here to here, then another integral that's going to go from here to here, and then another one from here to here. What's that?
It should be the same integral on the top most and the bottom most one. You just have to change the period of which it's integrating.
You're saying what? The same? These should be the same areas? What do you
No,
say?
like the
Oh.
same, okay, so like the top function, or the topmost, there's the top, middle, and bottom. The top and the bottom one are essentially the same integral, it's just the same.
Oh, yes, yes. Okay, yes, that's exactly right. The integrand, the part that's inside the integral, the integrand for this one and this one will be the same. It's the limits of integration that'll be different, yes. So why don't we call this one down the bottom integral 1, this one here integral 2, and this one here integral 3. What is it that we need if we are going to proceed? What pieces of information are we going to still need to get here? The intersections, right? We need to know where that hits, where that hits. Well, we already know that's 2 pi up there, right? So we know we're going to go from 0 to something, right? Then from that something to something else, and then from that something to 2 pi, yeah? Okay. So how do you figure out where these two intersect each other? Set them equal. We're going to set sine y equal to cosine y. When does sine of y equal cosine y? Pi over 4? 3 pi over 4? Yeah, you can just go back to your unit circle. Sine and cosine are the x and y coordinates, aren't they, on the unit circle? So you're just looking at where the x and y coordinates the same. It happens here at pi over 4, right? The x and y coordinates are root 2 over 2, root 2 over 2. And then it happens again down here at 3 pi over 4. No, that's not 3 pi over 4. That's 5 pi over 4. I think if you said 3 pi over 4, sorry, that's incorrect. That is over here. They aren't the same there, are they? They're off by a sign? Sine and cosine are off by a sign? Okay, so that doesn't count, but this one does. 5 pi over 4, they're both negative root 2 over 2, negative root 2 over 2. So only at pi over 4 and 5 pi over 4 they equal. And that corresponds to these 2 points. Understand? So this happens when y equals pi over 4 or 5 pi over 4. There's actually an infinite number of solutions because you can just keep going around, but we're only looking between 0 and 2 pi. Questions on those? Are we ready to set this up? Okay, let's set it up. It's going to be, I'm going to have to erase this. Just remember the blue one is cosine, the red one's sine, right? Blue is cosine, red one's sine. So integral 1 plus integral 2 plus integral 3 equals, integral 1 goes from where to where? 0 to pi over 4. And it's going to be the one on the right minus the one on the left, which would be, it's cosine y minus sine y. Everyone agree? Yes? Plus, now the next integral goes from, this time, pi over 4 to where? 5 pi over 4. But it's flipped over, isn't it? It's the sine y minus cosine y dy. And then integral 3 will be the same integrand here. This is what Ron was saying. Same integrand, just different limits of integration. So integral 5 pi over 4 to where? 2 pi of cosine y minus sine y dy. I'm out of room. Could you integrate each of these? Yeah, those are pretty simple antiderivatives. And then you have to plug in fundamental theorem of calculus for this, get an answer, get an answer, get an answer, add them all up, you're done. Dot, dot, dot. That means we're done. Last one. Do you get the basic principle of this, though? You've got to figure out what the region is, which is going to require some graphing skill, and then determine your limits of integration, plug in, you're done, right? All right, so let's try this. Sketch the region bounded by these curves and find the area. Y equals e to the x. Y equals 2e to the negative x plus 1. And then x equals 2. Just by looking, do you think you're going to use vertical or horizontal rectangles? Just by looking at what's up there. Vertical, because these are in terms of, they're solved for y, so they're functions of x. That doesn't always mean that, but that's what you're leaning towards here. So, drawing time. I've got a few here that I'd like to do. X equals 2. That's an easy one, right? That's a what kind of line? X equals 2. Vertical line going through 2. That's supposed to be straight. All right. E to the x, that one's not so bad, right? E to the x, we should all know what that looks like. 1 goes like this. Tapers down like that. And finally, 2e to the negative x plus 1. How about that one? 2 over e to the x plus 1. Is that not the same thing? It's the same thing. So what happens is, I'm trying to think if there's a number we could plug in that would be real easy to pick up on this. How about x is 0? If x is 0, what do we get? We get 3, right? E to the 0 is 1, 2 over 1 is 2, 2 plus 1 is 3. So at 0, we should be up here at 3. And now it's just a matter of trying to figure out what happens. As x gets huge, what happens? As x gets huge, this thing blows up. That goes to 0 plus 1. So the whole thing gets closer and closer to 1, doesn't it? As you go out to the right forever. Like this. Closer to 1, where's 1? 1's right here. So I'm getting closer to 1 as I go out to the right. Something like that. What does it do as I go to the left? If this right here, if x goes to negative infinity, e to the negative infinity actually becomes very small. And 2 over a very small number becomes a huge number. And so this becomes infinite, so it looks like this. Another thing you could have done, probably easier, is just to realize that e to the negative x is the reflection of e to the x over the y-axis. Much simpler to look at that way, but it's done. Do you see the region bounded by these curves? Yes? This it? Oh. Yes, this is it right here. Vertical rectangles going to work? If I draw a vertical rectangle in here, is it always going to have the same function on top as the bottom, and then same top and bottom the whole way through? Blue on top, yes. Black on the bottom. Blue on top, black on the bottom. So that should work. We need to figure one thing out, though. What's that? The intersection. We need to figure out where these two hit each other, right? The right side, we already know where it stops, don't we? We know that this integral goes from something to 2, right? And then it's 2 functions. What's going to be the one on top here? The blue one, e to the x, and the bottom one, 2e to the negative x plus 1, right? So we've got all of this already set up. We just need to figure out what this bottom limit of integration is. So we shall now do what to find their intersection? Set them equal to each other. And when we say them, we mean the two that hit each other, right? The blue and the black one. So we're talking about these two. So we set e to the x equal to 2e to the negative x plus 1. What would you like to do to that? Solve that for x. Natural log, I hear natural log a lot because natural log will actually, if I put natural log together with e, it'll wipe out and the x will pop out. Problem is on this side, when I do natural log, all of this is trapped in natural log and I can't simplify that. So it's going to trap x over here, unfortunately.
Can we change that one to
Change it, what?
e to the x over e to the x?
Change the 1 right here? Is that what you're talking about? Yes, you could. I think you're on to what you should do here. I'm going to write it this way, back like this. Yeah, you can just basically multiply everything, both sides of the equation, by e to the x to clear the fraction. So what happens if I multiply this by e to the x? E to the 2, wait a minute, hold on. No, that's right. No, I'm saying, but that was that problem on the test, right? E to the 2x was e to the x times e to the x. E to the x squared. Okay. We all know that now, right? We won't ever forget that. E to the 2x is equal to e to the x squared, right? We got that hardwired now, I hope. What do I get here when I multiply both of these by e to the x? 2, and then plus e to the x. All right, that's good. You cleared fractions. Now what do you want me to do? It's a quadratic form. This is basically a quadratic form right here. This, if we move everything to one side, looks like this. E to the 2x minus e to the x minus 2 equals 0, which is really e to the x squared minus e to the x minus 2 equals 0. So this is a quadratic form equation. Does it factor? Can this be factored? E to the x minus 2 plus 1. Do you agree with that? Do you all see that this is a quadratic in e to the x? Yeah? That if I multiply these back out, I should get this? Some people prefer it when I go in here and I make a substitution. I say u is e to the x. If I do that and rewrite this, the problem becomes u squared minus u minus 2 equals 0. And then I go through and just do like college algebra factoring on that. I'm doing the same thing. I'm just skipping all the intermediate stuff of this. Because this would factor to be what? U minus 2, u plus 1. And u is e, so this is it right there. So now that I have that equal to 0, I set each one equal to 0. I get one answer, e to the x is 2. The other one is e to the x is negative 1. How do you solve for x? Now you can come in with the natural log. You can come in and take natural log on both sides. So what do you get here? If I take natural log on both sides there. You just get x is natural log of 2, right? Taking natural log on both sides. And then the other one, when I take natural log of e to the x equals natural log of negative 1, you get x is equal to, natural log of negative 1 is undefined, right? Undefined. Can't put a negative in a natural log. So you only get one answer. You only get one solution. Does that match our picture? Those two only hit at one point, didn't they? So the answer is natural log 2. So that should finish up the setup for the integral. Right? It should be integral natural log 2 to 2 of, I forgot already, was it? It was e to the x on top, e to the x minus 2e to the negative x plus 1 dx. By the way, could you integrate that? You should be able to, right? Antiderivative e to the x is itself. Here we just distribute the negative, do it term by term. You should be able to integrate and plug numbers in, and it'll work out nice. That's the end of that problem, though, as far as what I'm going to do.
Do we stop here in the homework, or
Do we what?
do we stop at this point in the homework, or do we stop every day?
If you're going to want to try and match the book's answer, you go through everything. What I would do if I were doing homework is just set everything up first. You know, get it all set up for time's sake, and then go back and start evaluating them. Or do them all at one time. All right, you all look very, very exhausted today. Are y'all okay? Y'all just look all dragon. Not like fire-breathing dragon either. I mean like dragon. I have a stack of papers. Where are they? Are there any other stacks of papers floating around? So if you don't have, if you want to come try and retrieve your stuff, you can. Try and do your homework out of this section. See how it goes. You know what? Is it at the end of notes?
It should be.
Let me see, maybe not. Okay, let me tell you what to do then. This is off of page 369. Number 1, that's it, no. 1 through 19, odds. It's not so much. So on the first two, like numbers 1 and 3, they give you the sketch. So it's just a matter of you interpreting the sketch and setting up the integral, and then finding the area. The rest of them, sketch the region, decide either whether you're integrating with respect to x or y, which means are you doing vertical or horizontal rectangles. Draw a typical approximating rectangle. So they want you to like actually draw out. You don't need to necessarily do that, but if you want to, try and get this picture set up. And then find the area. See how that goes.
Well, what's the question right here? Like right here. So you put a question mark. I'm not sure why.
Okay, hold on. Let me turn my camera off. That's right. Excuse me real quick.